and I hope you're looking forward to this afternoon's session. I'm very pleased to welcome the first speaker. As this morning we'll have 30 minutes for the talk and then 15 minutes for questions, so do please think about your questions as we go through. And our first speaker is Professor Maria Clara Nucci from the University of Bologna, in search of hidden symmetries.
Thank you. Let me give you an outline of what I'm talking about. This is going to be, whoever was this morning is going to be a completely different type of talk, since I am a mathematical physicist, but I'm actually more, well, what am I more? More a mathematician sometime. With the physicist, I'm a mathematician. With the theoretical mathematician, I'm an applied technician, whatever. They ask me to repair a light bulb usually. Okay. First of all, I better introduce what I'm talking about. When I talk about searching for hidden symmetry, I better tell you which symmetries. An example, I would make an example because it's an example I like very much, since it was made famous by a movie years ago, and so everybody knows about it. Maybe not everybody, because if you were from this century or last century, you don't know the first, what was the name of that movie with the, I forgot, with the animals, dinosaurs, eggs. Jurassic Park, thank you. I couldn't remember. Okay, so I'm going to show you how to turn a butterfly into a tornado and vice versa, just an example. Then I'm going to talk about linearization of a superintegral system by means of hidden Lie symmetries. What's wrong? I know I make things very, very, how can I say, entertaining, but I'm not at the point that I don't know why do you laugh for. But that's okay. You'll tell me later. Then I'm going to talk about a famous phrase by Lagrange. Is mechanics a branch of mathematical analysis? The role of the Jacobi last multiplies, connection with first integral, Lagrangian, and Lie symmetries. Quantization, then. It's my last, yeah, I think it's the last one because I would run out of time. Quantization through the conservation of Nader symmetries. And I don't think I have time to talk about PT symmetry and the elimination of quantum bed ghost by a Nader symmetry ghostbuster. But maybe it's great because I don't know if I'll have time to talk about it. Let me start. Which symmetries? That's the point. Which symmetries? I mean, the previous speakers have touched the argument, this subject. So I'm going just to cite people. Here is Peter Olver's book. This is the first edition, then there was a second edition, Application of Lie groups to Differential Equations, Springer-Verlag, 1986. Historically, the applications of Lie group to differential equation pioneered by Lie and Nader faded into obscurity, just as the global abstract reformulation of differential geometry by Richard Tan gained its ascendancy in the mathematical community. 36 years later, and after hundreds of papers and many books have been published on this subject, the first by Ovsyannikov in 1962, more than half a century ago, Walter, a young analyst who studies PDEs, said, partial differential equation, the only useful symmetry is dilation. They can be used to determine embedding into Sobolev or Lebesgue spaces, and all other ones are useless. Michael, a senior mathematical physicist, instead, he said, what are these symmetries? Let me give you another citation, more recent. Hidden symmetry of dynamics in classical and quantum physics. Marco Carilla was publishing this paper in 2014. It was a review. And, quote, we point out that there exists another approach to the subject of hidden symmetries of the dynamics, which originates in the seminal work of Sophus Lie. Lie developed his theory of continuous group in order to find symmetries of differential equation that transform solution into solutions. The transformation act on both dependent and independent variable. Then he keeps talking about it, actually writing about it. And then he says, the theory of Lie group applied to differential equation can be cast in a form appropriate for Hamiltonian systems that is equivalent to the result we present. But in this review, however, we have chosen to adopt from the beginning the language of Hamiltonian system and phase space, which we think physicists and applied mathematicians might broadly consider as familiar territory. I am taking you into unfamiliar territory. Be aware. These two guys are Carl Gustav Jacob Jacobis, and the other guy with a beard is Sophus Lie. Carl Gustav Jacob Jacobis' contribution to the study of linear first-order partial differential equation inspired Sophus Lie. It was not only him, but there is a book by Hawkins won a prize many years ago, and it was about the birth of group theory and Lie group theory, who got convinced that an integration technique for ordinary differential equations meant the existence of certain groups of symmetry, known as Lie algebra or Lie groups nowadays. Lie methods has been successfully applied in different problems in physics. However, it has a major drawback when applied to systems of first-order equations. I'm giving you a bit of math, sorry. Ordinary differential equation of first order. I'm giving you the first differential equation that one encounters in any undergraduate program that touch math. This gamma is a linear differential operator, and it's called nowadays the Lie operator. Lie, of course, call it the group operator, but anyhow, his first prolongation, it's easy done by, by this gamma 1. I'm a bit, let me go this way. Here we go. But if I go this way, you can't hear me. Okay, forget it. Gamma generates a Lie point symmetry for equation y prime equal fxy, or y prime minus fxy equals 0, where f is an arbitrary function for the time being of x and y. And I don't put any theoretical analysis property on f. Anybody can look at Cauchy theorem just in case. If and only if the prolongation of gamma applied to this H equation along when H is equal 0 is equal 0. This yields the following determining equation. I want to point out that this is an equation, a partial differential equation, linear, even if the equation to start with y prime minus fxy equals 0 was nonlinear in f, but it's underdetermined. I have two unknowns and one equation, so it's useless. And it has an infinite number of solution. But if you are lucky enough to find one particular solution, then there is a link between Lie symmetry and an integrating factor or an Euler multiplier, as was used to be called at the time, because he made it. And to solve this first order ODE, and the link is in the formula, in the frame formula. Infinite solution means nothing. That's the major drawback of such a problem. Let me give an example from Leonhard Euler and himself. He was looking at this in this paper. He was looking at this equation, and it's a first order equation, and he found the integrating factor. He didn't write it in this way, because at the time you would have differentials, not derivatives, of course, in his paper, but I wrote it in the modern time. in the form of the modern time. And you have this integrating factor. So from this integrating factor, you can have this Lie symmetry from the formula above, before. A first order ODE, I repeat it, admits an infinite dimensional Lie symmetry algebra. But increasing the order decreases the dimension. So if you have, and I don't go into the glorious details, just to give you a glimpse of what it means to find a transformation that acts on the dependent and independent variable. It means to do something very, how can I say, algorithmically. It's very easy to do it. And nowadays, of course, with computer algebra, it's even easier because you don't have to do it by hand. And you get the second prolongation because you have to act on the second derivative if you have a second order differential equation. And here again, the second prolongation, apply it to the equation. When the equation is equal 0, gives you another determining equation, which is over-determined. Because of course, y prime, as you can see, is given by this equation. And so f contains y prime. So you can, this is something that is equal to 0. Before, you have two unknowns and one equation. Here, you have more than one equation because y prime has to be free. Otherwise, you have a first order equation, not the second order equation. So whatever is the coefficient of y prime should be 0. And the maximum number calculated by Sophus-Lie of a simple second order differential equation is 8. So 8 transformations are the maximum number of, I call, and not me only, Lie point symmetries, which are transformation of x and y that leaves the equation invariant. So it takes solution into solution. Having symmetry means solving the problem. I haven't talked about conservation law yet. Here is the example of the butterfly. This is Edward Norton Lorenz. And in 1972, he gave this famous talk entitled Predictability. Does the flap of a butterfly wings in Brazil set off a tornado in Texas? And he was talking about the left picture for you, which is these things that could be thought to be the butterfly wings. And on the other side, you have a sort of a twister, more than a tornado maybe, but anyhow. Let me give you how to go with symmetry from one to the other. Lie symmetry can transform a butterfly into a tornado and a tornado into a butterfly. This was a long 20 years ago paper of mine. Lorenz system is the red one. It's a 3 first order ODEs. If I had the problem with one first order ODE, that I have infinite symmetry, I cannot find algorithmically not even one, the things get worse if I have a system of first order equation. We are used to teach the student that you can take an equation of order n and transform it into a system of n first order equation, ordinary differential equation. And they are the same. It's not true. In terms of symmetry, it's not true. While a second order differential equation has a maximum of 8 symmetry, no more. Two first order ODEs that comes from the second order have an infinite number of symmetry. Get that. Now, in this case, this was very simple. There was an integrable case with the sigma tilde, r tilde, b tilde are the parameter that were in this model. This model was derived by Lorenz in 63. It's written there, 1963, and he was a meteorologist, not the Lorenz that was mentioned before. And he noticed that there was something wrong in changing the initial condition of this problem. And he was numerically trying to solve it at the time. But Seguri, I say in 1980, found some solution of this problem for particular value of these parameters. And one of them is this third order ODE, this equation, system, as you can see, sigma tilde is 1 over 2, R tilde is 0, and B tilde is 1. And the corresponding third order equation gives you two symmetries. Of course, I said second order, maximum is 8, third order, maximum is n plus 4, so it's 7, but actually you have just two symmetries. Of course, if you write the equivalent system like it's written there of 3 first order equation, how many symmetries? An infinite number, forget it. But now, by raising the order, you get two symmetry. What can you do with these two symmetries? Nothing for the time being. Well, you could integrate it in terms of elliptic function. Okay, fine. But, see, I teach mechanics, rational mechanics, analytical mechanics. Rational mechanics comes from Newton, and before him from Pappus, but anyhow. And Euler had this famous book about rigid bodies. Now, I was trying to think in English, but I come in Italian, and so it's a bit confusing to me to talk in Latin if I talk in English. But anyhow, fun enough. And this is the case of a rigid body with a fixed point free from torsion. That's what we would call it. And it's called the Euler-Poisson system. And you can actually integrate this one, is integrable. And the third order equation admits two symmetries. Here they are. And dt and this tdt minus pdp scaling. And then you can look at those two with the previous one, and they are the same algebra, Lie algebra. It's type 4 in Lie's classification of the real two-dimensional Lie algebra in two variables. Number 4, there were 4 only, so 2 abelian and 2 non-abelian. So you can link them. You can put together those, and you can go from one to the other one. And this is the transformation, tau x, y, in terms of t, q, p, q, and r. Now, there is also, which probably at the time I confused people by doing it, but there was also a link between the inertial momenta. So you see this B and A and C to make it match. And the transformation goes from 1, and then you can invert it. I want to show you, actually point out to you that there is a transformation of time. And time, the transformation, is inverting the time, and also there is an exponential, so things are not quite physical. What happens if one applied the above transformation to the general Lorenz system? This is the Euler-Poisson system with this B transform. And you can see that now I have, with this transformation, I have a momentum, which depends by the components of the angular velocity and time, by the way. And here is a tornado. So if you do the numerical with the same type of parameters to this one, because you see inside that equation now you have the R tilde, B tilde, and so on, you get the tornado. So, and there is no chaos, because whatever was the problem is now in the eye of the twister. So just the beginning, well, I move forward and I don't take the same. So this is a bit of a joke. Let me see a bit more in deep what a complete symmetry is. This was an idea, but I don't know if it was completely original, by Krauss in '94. He extended a notion of symmetry in mechanics and to characterize a classical system by the symmetry law it obeys. Namely, different mechanical systems cannot have exactly the same symmetry property. And when I talk symmetry, I talk about transformation. But to do that, introduce non-local symmetries. And as you can see, this Y, this red color formula, you have an integral, psi in dt. And then he applied that to the Kepler's problem, and he got 3 non-local symmetry of the Kepler problem, 2-body problem, the usual one. And they are this, I just put y1, but you can put y2 and exchange x1 with x2, and then the next one, you took all the permutation. I was curious about it. When I see that, I look for hidden symmetries. Which are the hidden symmetries in this case? Transform the system of three ordinary differential equations, Kepler problem, in 6 Hamiltonian equation or 6 first-order equation anyhow, and then do what Jacobi taught us to do when he was solving the Euler-Lagrange top. What did he do? Well, I mean, the equations are autonomous. There is no time. So why bother to take time? Take one of the dependent variable as the new independent variable. And if you do that, you get the symmetry that were with the integral are not anymore with the integral, are just point symmetries of the underlying equations. Great. I go to another subject now, superintegrability and hidden symmetry. I assume, but I'm not sure now, that Liouville theorem about integrability is one of the basics of Hamiltonian mechanics. And Liouville, actually, it was not Liouville really, but I leave that to the historian. There was another paper, but Liouville said, well, I did it too, but I'm happy to have the young one to publish it in my journal, which was the Journal des Mathématiques, the pure and applied mathematics. And he said, if you have an autonomous Hamiltonian system, and you have, say, 2n, twice number n integer, number of equations, and you know n first integrals and conservation law of the system, then you can integrate the system completely. And I'm not going into the glorious detail that this first integral have to have their Poisson bracket to be 0, 2 by 2, and if it's independent, they have to be independent of time. That's the major thing. Or everything independent of time. Of course, I'm not going to the Liouville-Arnold theorem, which means that I have to have a torus because the system of the n first integral autonomous are actually a connect space and a compact space. So this is more into the topological argument or in differential geometry, if you like. But anyhow, superintegrability was born in quantum mechanics. It was not born in classical mechanics. And, but there are a lot of, produce a lot of papers, even in classical mechanics, and we see some of it. I just point out this one because it comes out from a paper by Drach, D-R-A-C-H, in the 1930s, and one of these cases is the one that I show you here that was discussed by Sarah Post and Pavel Winternitz in this paper in 2011. And then I decided to involve Sarah Post. We were on the train going from one conference to the other conference, and say, let's look at this from the point of view of hidden symmetry. You have Hamiltonian equation, U1 dot, U2 dot, blah, blah, blah. 4 equations, first order. How many Lie symmetry? Infinite. Okay, right. There are 2 first integral. They already found 2 first integral. That's why it's superintegral, because the Hamiltonian also is a first integral of conservation law. And they are all autonomous, and the Poisson brackets is 0. They are invariant. Okay, fine. What's about property of this system? I'm going to show that this system, through hidden symmetries, actually, and it's not separate. I mean, the Hamilton-Jacobi equation, for whoever is a bit familiar with that, does not separate in any coordinates. That's important. So, and you look at these two first integrals, you are scared. There are u1 to 2 third. How are you going to solve it? Okay, let's go back to the Lagrangian equation of this system. Two second-order equation. They have only two symmetry. We know it. Okay, dt gives you the Hamiltonian. The other one is actually the damn, sorry if I say that word, scaling that never gives you anything. Unfortunate, with naders, of course. Since systems like that, the previous one, the Hamiltonian, or the, if you like, the four first-order equation, is autonomous, we can choose one of the dependent variable as the new independent variable. For example, u1. And here is, instead of 4 equations, I have 3 equations of first order. Already, it's impossible. Eliminating one of the dependent variable, for example, from the second equation, then the system becomes this ugly stuff, but this ugly stuff emits 10 Lie symmetry. And which implies the system 1 is linearizable. And to go further and finish it up like that and keep going, it's with the next topic, is actually this. It hides a third order linear equation, a trivial one. And you can go back and do the symmetries for the system. But since I am running out of time, I was going to show you that you can get conservation law without the Nader theorem, thanks to Jacobi. I've done other things with other people, Peter Lee, Giorgio Gubbiotti, so to show that there is linearity underneath superintegrability, thanks to hidden symmetry. Going down, check for them, find them. So, for example, today somebody was mentioning non-Euclidean spaces. Even in the case of non-Euclidean spaces, you can find linearity, linear equation underneath it all, these superintegral cases. Look at this, for example, this ugly Hamiltonian. You can imagine how ugly are the equation. And now with Ludwig Campoamor, we have already gone into 3-dimensional Euclidean space and find out they are actually all linearizable, the one that were found by Evans in 1990. I know, I'm just trying to fire them off, all of them, and find the linearity that it's underneath all this superintegrable system. Let me skip all of that because it's, okay. Lagrange, just that. In the advertisement of the Mécanique Analytique, I think that sorry, I forgot the name. The second speaker today was mentioning Lagrange, but he was mentioning Mécanique without an H. The H one was the first edition, and in the first edition, Lagrange said, the methods that I explain in it require neither construction nor geometrical mechanical argument, but only the algebraic operation inherent to a regular and uniform process. Those who love analysis will with joy see mechanics become a new branch of it and will be grateful to me for thus having extended this field. Sorry, it's a joke. Come on, it's a joke, isn't it? Isn't it? No, it's not. Jacobi last multiplier. We forgot about Jacobi last multiplier. Now it's coming back, lucky, I mean, also because of me looking at these things. And Jacobi last multiplier is a multiplier that links two things that are 0, okay? And this multiplier, remember one of the reviewer didn't understand what I was doing, of course, and instead of looking at things, he said, well, why bother? You are doing, complicating the stuff. No, I'm not. Because if I have two multiplier and solving this equation, their ratio is the first integral. And how many Lagrangian does one know? Okay, Mr. Jacobi told us that a multiplier can give you a Lagrangian for a second order equation. So how many second order equation, how many Lagrangian for one second order equation you can find? An infinite number. Forget physics. Enter Lie, and that's important because otherwise, how do you find the solution of this Jacobi last multiplier equation? Lie was studying his work. And he put that into context with symmetries. So just give you a simple example. xw dot equals 0. It has 8 symmetries, okay? 2 first equations, just because first order, it has infinite, but we just take 8. And with 8, we just calculate 2 by 2 all these determinant. A determinant will give you a Jacobi-Las multiplier and actually conservation law as well. But look how many Lagrangian you get. You get about 10 Lagrangian. And finally, you get the true Lagrangian. So how do you physically eliminate 9 out of 10? Okay, this is easy because it's a second order differential equation everybody knows. No. How do you do it really? You call Agatha Christie, I think, that in the theater in Oxford there is the mousetrap. No, they differ by the number of nether symmetries that they admit. The physical Lagrangian admit the maximum number of nether symmetry, which is 5. However, also other 2 Lagrangian have 5 nether symmetries. So how do you eliminate? Well, you ask nether and Schrödinger, and Schrödinger will help you. I'm going over time, so I'm just going to tell you how to do quantization, going from classical to quantum mechanics. And when I say quantum mechanics, I just say I'm not going to be bothered, I'm just searching for a time-dependent Schrödinger equation, okay? And it's known. What is known? Well, if you look at the symmetries of a partial differential equation, which is the Schrödinger equation for this one, the simplest Schrödinger equation, the blue one, the simples. Well, you see the x1, x2, x3, x4, and x5 are nothing else than the nether symmetry of the true Lagrangian of xw dot equals 0. So you can actually use that, plus you have, because it's linear, you have, one alpha deep psi transformation. Of course, it's linked to the solution of the Schrödinger equation, but that's not the point. The point you can go, well, Marcos Moschinsky was, I think, he won the Wigner medal. I know he won the Wigner medal. The first one to win the Wigner medal was Wigner, and then the second one was Marcos Moschinsky. How to obtain the Schrödinger equation? Same thing. So how do you quantize? You find the Lie symmetry of the Lagrange equation. You find the nether symmetry. Construct the Schrödinger equation admitting those Lie symmetry, look, in the space and time part. And then the psi part will come. Plus the usual quantize preserving the symmetries. An example, I give an example from population dynamics. Today, a few months ago, I've seen some announcement in the Mathematical Institute about 2 postgraduates being hit on the road to Northfjordeid, which is the place where Sophus Lie was born, so can't say on the way to Damascus. And they wrote a paper how to, in a way, exclude between 2 models in cancer, which one has the best symmetry. And when it talks about symmetry, they talk about the model and they talk about Lie symmetries. And I'm very, very happy about it because I wrote a paper applying symmetry to biomathematics, epidemics, and it was always rejected. Of course, that was last century, so now, of course, we are not. So this is the complete symmetry group of this equation that comes from a biological point of view, but is any equation, and you can actually write, because of the complete symmetry group, a precise Schrödinger equation for this equation. I'm not going about all the other one in more than one variable, of course. It's the same, you can find that. And I'm just going to finish because, that's the last one. You remember that I was talking about the 3 Lagrangian for the xw dot equals 0. How do we eliminate the wrong Lagrangian? I say nether is not enough, but Schrödinger may help. Well, if you take the one that we know is the right Lagrangian, 1 over 2x dot square, you get, applying by this method, you get the right Schrödinger equation. What happened with the other ones? Well, one will invert space with time. It's a simple mathematical joke, I think, talking about Lagrangian making a joke. And the other one takes you back to the original classical equation. So I think I'll finish here because my time is gone. Thank you. Thank you for your attention.
Thank you very much. We have a little bit of time for questions. If anybody wants to pick up anything.
I bet I shock everybody.
I think you may have done. All right. Well, I have a question on the Lorenz equation. Lorenz was worried about predictability. I mean, does the existence of those symmetries shed any light on the predictability question, or are we asking a different question?
This one was just a way to put together by symmetry two equations in two different fields. Because by accident, I'm sorry to say, that was quite by accident. Because I just look at the two things and I say, hey, wait a minute, this seems to be the same algebra. And that's why. And then when I did the numerical of the chaotic case with the flap, with the butterfly, I get this twist. So that's it. And as one editor put it up, it's very interesting, but there's no physical application. Can't help it.
Chance for questions?
I think I shock everybody with the mathematics. I
think
knew
you
that.
have. But yes.
Actually, I have a question. So thank you very much for this talk. I wanted to ask, how many hidden symmetries in the physical systems do you think we have? Because it seems that, I know that you haven't named them, but in physics we are aware of a few of them, like in Kepler problem, like two-body problem, etc., etc. But there are not too many of them. Do you think that there exists thousands of them that we are not aware of them, or not?
They are there. The problem is, okay, let me give you an example. You know that there was the golden rush. Sometime there is a golden rush for something. And people run to buy the last iPhone 22, okay? Now, the point is you go and stay online overnight in the only shop in town that sells iPhone 22. Then you arrive there and they say, we have finished it. Shut, boom. And you're helpless at that point. The same thing is with symmetries. Symmetries are there. They are underneath. We don't know how to find them. That's the point. So one of the ways to find them is this idea of transforming the equation. See, one of the things that it's sort of, and here we were talking about different models in physics, and I'm sorry if I go the other way. I said, why do you want to be stuck with it? Why don't you look instead of the symmetry, like the young people here have done, which I'm very happy, stuck with the symmetry. The complete symmetry group, for example, is a very interesting question. Some years ago, there was a paper in, I think it was Science, I'm not sure it was Nature. It was one paper and the guy said, let's get rid of equation. Let's get rid of differential equation in physics. It was this paper. I mean, it was published. Well, in a way, with the complete symmetry group, you don't need the equation. Because the only problem is that you have to find them. That's a good question. Of course. Why do you want to stop doing research? Let's find them, number one. And number two, when you have that, you don't have one representation, you have plenty of other representation, maybe. And you have to be sure, but you have to be sure that that equation is represented by those symmetries and not by other symmetries, because otherwise you get nothing. And the point is, I mean, Nail Ibrahimov was, unfortunately, I used the word was, he died a few years ago, and he was used to say, chercher, I mean, my French is nil, so chercher le groupe. So instead of chercher la femme, chercher le groupe. Or chercher les how do you say man in French? That's funny, I don't know. Men? So, and the point is that it's been always, I mean, there are a lot of people, for example, Hans Stefani in Germany, he was a general relativity, and suddenly he found out about symmetry. And he wrote a book. These two postgraduate students, one from Sweden, one from here, I think, they were both in Oxford. They just found in August, so it's very recent, it's in the website, this idea. They found out about symmetry. They didn't know anything about symmetry because it's not part of the education. And I am very, very, very upset about it because you miss a tool. Who was talking about different tools? Why do you want to use the usual tool? There are tools there. I mean, Einstein used a tool that was already there, right? Levi-Civita was the expert of that tool, and he didn't know. I mean, then in the end, he said the only one who understood general relativity was Levi-Civita, and not by accident. I hope I replied to your question, or I answer it somehow. Thank you.
Thank you. Oh, we have a question down the front here. So just time for a quick question and answer, I think.
In several examples, you showed us that hidden symmetries can lead to the linearization of the equations, and that means in the end to the solvability and the computability of the problems. So my question is, how much is the influence of these symmetry arguments in algorithmic theory nowadays, computation? That means what may be the help of these hidden symmetries for, in the end, for computer science?
I don't like to touch the computers. I don't like to touch artificial. You are talking about artificial intelligence.
Linearization means you can solve in the end the problem, and it's computable in the end. Which may not be the case if it's highly complicated. And that is due to the discovery of hidden symmetries. I thought that was the message of your, of a part of your talk. And so my idea is to analyze how much is the influence of symmetry arguments to computability in general. How can it be helpful for computer scientists, for example, to solve very complicated problems in order to make them realizable?
Well, I must admit that you're touching a very, very dangerous terrain because it's a quagmire. Because there are scientists, computer scientists with artificial intelligence, they are saying we'll give up with the brain. We'll give up the human brain. And so they think that just by putting data in the computer, they can get Kepler, well, I don't know, say something, Schrödinger equation, no, it's too easy maybe. Or, where are you? Maxwell equation, electrodynamics, they can get everything just by fitting up the computer with data. I raise my hand and I say, it's like to have, how can I say, an unknown, a quagmire there. I'm not know anything about it. I don't want to be involved with it. I let everybody who wants to be involved with it, but not me. I am more into the human brain, and I don't think, and it's not my human brain. It's not only your human brain. It's everybody here in this room, because science is collaboration. It's not pushing a button in a computer. Sorry. I mean, for me.
As one of the computer scientists in the room, maybe I should stick up.
No, that's what I say. It's collaboration. But I'm talking to computer scientists who are saying, I feed up the computer with data analysis, with data, and then I get Kepler. Good.
Yeah. Okay, well, let's thank you for those answers. And
say nothing.
Let's thank the speaker, and we'll thank you.
Thank you. Thank you.